righty. Matthew, can you hear me?
Yes, Professor.
Awesome, thank you. Okay. Behind this. Okay, and can you see the OneNote?
Yes.
Great. Okay. So we're pretty much gonna get started on the last live lecture for the semester, in which we'll cover integer programming and really more focused on mixed integer linear programs. And this is the last topic that we really need to cover in order for you to complete your project or the extended assignment. Now, that said, at least on the theoretical side, that said, there are some sort of practical, technical skill-based skills that you'll be required to have in order to implement your project in CPlex. And so those will all happen through CPlex videos that I've posted or will be posting for y'all. So again, in order to complete the extended assignment / project, you will have to watch those videos. And sort of the corollary to that is in lieu of lectures for the next couple weeks, you're going to be expected to watch those videos. So, you know, unfortunately, some students have some difficulty in sort of self-managing their work for this last month of the class or the last few weeks of the class. I want to highly encourage that you guys not have that problem. As a general rule, the week before the project is due, I will not be spending time with students on very basic CPlex issues, right? So if you're asking me, how do I do a for loop in CPlex? Or how do I read in data into CPlex? You know, to be honest, it's not exactly an appropriate question to be asking the week before a month-long project is due. And so I'm going to refrain from answering those questions. So I highly encourage everyone to start working on the project as soon as possible, pretty much next week, and to start doing all the videos so that as the next month progresses, you know, prior to December, so in the next 3 weeks, you can get out all your questions that you have about implementation or formulation. Really, you know, you should be leaving that last week for the more advanced or some of the more technical issues. Just a heads up there. Okay, so with that, we're going to start our discussion on integer programming. So to date, our focus, and I'm going to turn off my video because I don't think it's particularly useful if you see the top of my head. Let's see. And we're going to hide meeting controls. All right. So today, our focus has been in the area of linear programming. So usually when we are solving an optimization, we are looking at some sort of minimization or maximization subject to some linear constraints. And, you know, we might have some non-negativity constraints, not necessarily required. But the most important part was this assertion that our decision variables actually came from the real set. Okay. So we assumed continuous real variables. Now, this actually places quite a constraint on the type of optimization problems that we have. Well, not quite a constraint, but, you know, it is a meaningful constraint that it's worth addressing, where sometimes it doesn't make sense, right? So when we talked about our furniture problem and we decided how many chairs, tables, or desks to make, we formulated it assuming that the decision variables could be continuous. So we could produce 10.5 chairs or 11 and a third tables. But we didn't really give much thought to what that meant. So here in this lecture today, we're going to start putting constraints on the decision variable x in a variety of ways. So one of those ways, so we'll still write, our cost equation as C transpose X. Maybe we even have a quadratic term, right? Doesn't really matter. We will also still have a linear term here, and of course we can even have a quadratic constraint. This is within the realm of what we've discussed before. Okay. Now what we're going to add in is we're going to say, maybe some of these decision variables, they have to be integers. So for those of you who don't know, this fancy Z is how we write the set of integers, right? It's sort of the same idea as writing the set of reals up there. Alternatively, we might say that some of the decision variables are binary variables. Oops, not are. This gets written a few different ways. Sometimes people will write a funny B. Alternatively, you'll see people write 0, 1, right? So these guys are binary variables. And in fact, nothing precludes us from still having real variables. So we might say some of our decision variables are still real. Or continuous values. When we have multiple types of decision variables, we call our program a mixed integer linear program. So specifically, we do need real, and then you can say, well, we can have integer or binary. Really, binary is just a subset of integer, so it's not that different. And again, we call it a mixed integer linear program, MILP for short. And again, maybe this isn't necessarily linear. This could be quadratic. Right? In which case we'd be talking about I don't know how you'd pronounce that. MILP. Who knows? We could talk about a mixed integer quadratic program. Okay, so again, the issue that we're dealing with, I think the sort of standard problem where we'd say, well, this doesn't really make sense, was that furniture problem, right? we had decision variables that related to the number of desks, right? Number of chairs, number of tables that got produced. And previously, we had assumed these DVs were continuous variables. But now we want to stop that, right? So, you know, if we had a decision space, I think, I think at the time our decision space looked something like the following. Who knows? It might be something like this. And we said, well, everything inside this area is a reasonable solution, and we'd take our ISO line, right, and corresponding to the objective function, and we'd move it up into this region, and we'd see where the last point was, where the ISO line was still within the feasible set. Now, the reality is, because the number of desks, chairs, and tables that we can build are integer, really, our solution could only lie at maybe these yellow points, right? And so it was possible that we ended up generating solutions that were not feasible, right? So, these red, I'll say these red ones are outside of the set, the feasible space. Right? So if we ended up with a, let's say, let's say on this problem, we ended up with a solution right here on this vertex that was infeasible in the integer space. And we'll just say practically infeasible. I don't know. I mean, it's feasible for the linear program, right? But practically infeasible because we can't build, half a table. And so because it's not integer, it's not practically feasible. All right. So this is where mixed integer linear programs come to the rescue. All right. So again, with a mixed integer linear program, so we have a MILP, we're going to have continuous decision variables. We'll have integer decision variables, potentially, or binary decision variables. And again, usually, really binaries in some ways are a subset of integers. Binaries is just 0 or 1, right? But we use 0 or 1 oftentimes to represent a logical decision of true or false or yes or no. In that context, we can think of our optimization still as, C transpose times X, subject to AX is less than or equal to B. But in this case, our decision variable X might be broken up into a few different parts, right? So where X contains some real decision variables, it might also contain some integer decision variables and also some binary decision variables. And here NR, NZ, and NB just correspond to how many of each of these types that we have. So our main decision variable is X, and again, it's sort of built up of real decision variables, integer decision variables, and binary variables. Okay. so what I want to do is give you a quick example based on a paper that I had written a few years ago that sort of aligns with this idea. And in fact, it's also closely related to your project, except, I think you guys are solving a slightly different problem. Okay. So what I'm going to describe here is a typical airport problem. Okay, so you have a runway, and here goes your tower, right? And you have a terminal over here. Okay. And what's going to happen is, all these airplanes, let's say in the morning rush, they're going to want to line up. They're going to line up in order to take off. Okay. So all these airplanes are going to line up. Okay. So we'll have one airplane here that's a triangle, another airplane here that's a triangle, another one that's a triangle, and let's say another one. Okay. And they all want to use the runway in order to take off, right? So this is a departure runway. Now, in order to have safe operations, you can't take off two airplanes at the same time. You can only do one at a time. All right? So we're going to have to time these airplanes to take off, right? Now, the problem with, or one of the added difficulties is that the timing between aircraft is not the same for all aircraft pairs, right? So let's say you have a really big aircraft that's taking off. What actually ends up happening is it generates something called a vertex or a wake, I guess. So imagine if you've ever seen a boat in the water, behind the boat you see the waves it creates. Well, airplanes do the same thing. They generate a wake behind them that's turbulent, except it's wind. And the problem is if you have a small little airplane right behind it, that airplane will actually flip over if it gets caught in the wake of a larger airplane. So what ends up happening is if we have a big airplane, then we're going to need a lot of time between the big airplane, when the big airplane takes off and when the small airplane takes off. The reverse is true if we have the small airplane first and the big airplane second. What happens is the wake off of this small airplane is much smaller. But not only that, because the big airplane is like very heavy, it's not affected by the wake of a small airplane very much. So let's say between a big and a small airplane, maybe you require 6 nautical miles separation between when the big aircraft takes off. You have to wait for it to travel 6 miles before the small one can take off. In this case, where we have a small airplane followed by a big airplane, sometimes this can be cut in half down to 3 nautical miles. Okay. Now, for this particular problem, I'm going to describe it in terms of time, just to make life a little bit easier. So instead of saying 6 and 3 nautical miles, let's say it's, 2 minutes and 1 minute. Okay. So we're going to formulate this problem all in terms of time. So for aircraft I, so this is aircraft I and aircraft J, their required spacing will be given by a variable, or not a variable, a constant Tij. So this is something that's usually given. Right? The other piece of information that we're going to be given is the scheduled time of pushback. Okay. So we'll have their time that they need to be separated. For each AI, we have a pushback time. And we'll call this, you know, TBI. Okay. So that this pushback time corresponds to the time that an aircraft pushes back from the terminal. From there, each of these aircraft is going to have to taxi to the runway. So depending on how big the airport is, the time to taxi to the runway could be different, right? So each aircraft will also have a TTI, which will be the taxi time. And so this is the pushback time. Right. So we have a taxi time, and we'll denote this again, TTI. Okay, so what's the problem? Well, the question that we're going to ask is there a way that we can reorder these aircraft? So maybe we'll make some adjustments to the pushback time, right? So we have this desired or scheduled pushback time, but what if we want to make adjustments to the pushback time so that we can actually get a greater throughput on the departure runway, right? Because the idea is, you know, with this spacing requirement, you want to be careful on how you order the aircraft. You're much, you know, if you're saying, well, we have a big aircraft and a small aircraft that are about to take off, this situation would be undesirable, right? Well, this one would be more desirable. Okay, so we might want to do some reordering of the aircraft. So the question is, how can we do that reordering of the aircraft by adjusting the pushback times? Okay. So we're going to define what did I call it? TAI, which to be a decision variable that adjusts pushback times to help optimize operations. So in this case, the way we'd optimize the operations is minimize the total time for all aircraft to take off. All right, so let's sort of see how we do this. Okay. And along the way, we're going to have to define some additional decision variables that help us keep track of everything. So, but we have most of the basic information here. So to start with, I'm going to introduce a new decision variable. And this is just going to help make our life easier. And we'll call it TTI. And this is going to correspond to the time aircraft I takes off. Alrighty. We can calculate that takeoff time according to the variables that we have. Well, so how do we do that? Well, the takeoff time for aircraft I, that's equal to the desired time of pushback plus any adjustment in that pushback time, right? So you could advance or delay the time of pushback. So again, this is, let's say, estimated or desired pushback. And it's a constant. Here is our decision variable, which is the adjustment to the pushback time. And then, and then we have the taxi time. Okay. Now this isn't exactly right, so I'm actually going to change this to be greater than or equal to. Okay. And you'll sort of see why I'm having to do that. So, because what's going to end up happening is we're going to have this additional time where the aircraft is waiting to take off, right? So maybe they get to the runway, but there's an airplane that's going to take off before it, and it's going to have to wait. So we can either explicitly encode this variable or we can not, right? So if we don't include this waiting time, then we'd use a greater than or equal to, okay? Now, if we do include it, so I'll just say not including wait time. We could set it to an equality, but I want to be a little bit careful in doing that. So I'm just going to leave it like this for now. Okay. So what we're saying is the takeoff time is greater than the pushback time plus whatever adjustment and the time to taxi. Okay. So this next part is where we begin to introduce our decision variables. Right? So let's say we had 3 aircraft that we were scheduling. Right? So we had A1, A2, and A3. Right? We could actually have these go in a number of orders. So, so let me move this. We could have that order go A1, A2, A3. We could go A2, A1, A3, A2. Oh, actually, I should do this in order. A little more systematic. We could do A1, A3, A2. Alternatively, we could start with A2 and then go A1, A3, A2, A3, A1. Or we could start with A3 and go A1, A2, or A3, A2, A1. And so these are the 6 different combinations, or 6 different orderings that we could have for these aircraft. And the question becomes, well, what ordering should we choose in order to minimize the takeoff time of the largest aircraft, of the last aircraft? Okay. All right. So if we think about this takeoff time, right, so we have this idea that we can calculate the takeoff time for each aircraft. What we can then do is we can say, well, we want to minimize that maximum TTI, right? Now, this is just the same thing as saying, well, we want to minimize the L infinity norm. Okay, so this is pretty easy to do. We've learned how to do that before. All we do is we'd introduce a new variable, and we can call it TT max. Right? And we would say, well, TT max is greater than TT1. It's also greater than the takeoff time for the second aircraft. And third, fourth, fifth, all the way up to the nth aircraft. So in this way, if we minimize the maximum takeoff time, effectively what we're doing is we're minimizing the last time or the last takeoff time of the aircraft. And so in this way, we're optimizing our takeoff operations. Okay. So this is sort of the structure to minimize the time required for the operation. And by operation, I mean a takeoff, right? So if I'm minimizing the operations, then I'm minimizing the time required for executing all the takeoffs. Okay, so that's the structure how we do it. Now again, we need to sort of define, well, what are these TT1, TT2, TT3? And this is pretty easy to do. We already have that equation, so we can stick it in there. So I'm just going to write it in the more general form, which says TTI is greater than or equal to T pushback I plus T adjust I plus T, oops, and did I I'm sorry. I used two TTs. One of these should be for taxi. I'll make this a capital T. I know that's not really, it might be a little bit confusing, but we'll make this a capital T as opposed to a lowercase t for taxiing. So again, this capital T is for takeoff. I should be more careful about my decision variables. Okay. All right. So we have an equation to describe how we calculate the takeoff times. And this is true for all I and 1 to n for these n aircraft. Okay. So finally, we have to get to the hard part of this problem. All right. And the hard part of this problem is, how do we decide the ordering of the aircraft? So I said we have about 6 different ways that we can order the aircraft. And one way that we can go about doing that is we can introduce binary variables that describe the ordering. or the ordering decisions of aircraft. And effectively what we're doing is we're introducing a new binary variable, or new binary variables. So in this case, we can introduce a binary variable, let's say call it B12, right? So if we have this 3 airplane case. So B12 corresponds to aircraft 1 taking off. So actually, B12 will describe the order, the takeoff order between aircraft 1 and 2. Right? And what we're going to say is if B12, it can take on 2 options, 0 or 1. Actually, I'll do 1 and 0. So it's going to be equal to 1 if aircraft 1 takes off first. And it'll take on 0 if A2 takes off before A1. Okay. In a similar way, we can describe binary variables B13 so same idea as above. So this binary variable will tell us the order between aircraft 1 and aircraft 3. It will be equal to 1 if aircraft 1 takes off first. Okay, so we're going to use that sort of label where if the first integer or the first index corresponds to true, right? We could also do B23. Okay, and again, this will be the ordering between aircraft 2 and aircraft 3. Now, in this case, we don't actually need, so if you only have 3 airplanes, you don't actually need a binary variable for, let's see, 1, 2, 1, 3, 2, 3. We don't need binary variables for B21 or B31 or what is it? B32. And that's because B21 would be the negation of B12, right? So like if this, the way we index it is, does aircraft 1 come first before aircraft 2? Then this idea of B21 is just the flipped logic. So we only need one of them. So if we know B12, that tells us about the relationship between aircraft 1 and 2. We don't need another variable to tell us that relationship in the opposite order. Okay. And so for that reason, that's why we don't have, 6 binary variables, right? We actually only need 3 in order to fully describe all these ordering options right here. Okay. All right. So let's see how we can use these binary variables. Okay. And we're going to focus in on first B12. So the question is, how do we use, let's say, Bij how do we relate the Bij to the takeoff times? Well, we do something like this. Yeah. So let's say B12 is 1. Right? And what we mean to say here is aircraft 1 takes off before aircraft 2. If that's the case, then that will mean TT1 is less than TT2, less than or equal to. Okay. So again, this is a time, let's say from 0, so a smaller number means it takes off first. All right. Now, if B12 is equal to 0, then that means A2 takes off before A1. In this case, we would have TT2 is less than or equal to TT1. All right, so that's good. So we sort of have this relationship between the binary variables and a linear constraint. We just need to fill in one thing, which is because of this wake category, or sorry, this wake turbulence behind the aircraft, we have to make sure that we have sufficient time between one takeoff and the next. Right? And so the way that we would add that in is we would say, well, if aircraft 1 takes off at 1 p.m., then aircraft 2 can take off a few minutes later, and that time is given by the delta T12, which we had described all the way up here, which has to do with the aircraft spacing. Okay, so this is the delta Tij. Okay. Now, similarly, if A2 takes off before A1, we have the same equation, but instead of using delta T12, we're going to use delta T21. And again, this is a constant value, which will be, which is predefined, right? It's not going to change. It's not a decision variable. At this point, our only decision variables, at least in these equations, are the takeoff times. And in fact, this binary variable is going to be a decision variable. Now, we can write similar equations for each of these options about the ordering of the takeoff times. So we're going to have B12 for the relationship between aircraft 1 and aircraft 2. We'll also have B13, and here we'll generate a very similar set of equations, but in this case, we'll just index it right between aircraft 1 and 3. And finally, the last set of equations that we have relate to the ordering between B2 and 3. Okay. All right, so we have at least a logical ordering of how we relate binary variables to linear constraints. The question becomes, how do we actually implement this in Cplex? Okay. And there's actually a few neat ways that we can do this. All right. So for starters, I'm going to sort of rewrite this in a different form that, hopefully summarize it. So I'm going to copy what we had before. So this is what we had before. And I'm going to add in sort of this idea of the binary constraints. Right? And I'm just going to write it in a logical way. So this isn't necessarily how you'd write it in Cplex, but the idea is similar. Okay. So I'm going to say if, and I'll highlight it in red because it's a little bit different, and this is sort of a non-standard way of writing things. So if Bij is equal to 1, then Tti plus delta Tij is less than or equal to Ttj. And this is true for all I less than j. Okay. Again, where I comma j is from 1 to n. Okay. So why do I have this I less than j? Well, if you look at sort of the pattern that we had developed before, where we defined these binary variables, we only needed 1, 2, 1, 3, and 2, 3. And the first index is always less than the second. And we said we didn't need the binary variables going the opposite direction because they represented the same idea, right? Of which aircraft goes first. So because of that, I can sort of simplify or understand that my I index is always less than my j. So the first aircraft is always in reference to the second aircraft, which has a larger index. Right? So that's why I can sort of write this constraint equation as saying, well, this has to hold true for all pairs of aircraft I and j, where I is less than j. Now, alternatively, else, if Bij is equal to 0, then Ttj plus delta Tji is less than Tti. Okay, and again, this follows the same sort of pattern where I has to be less than or equal to j. Now, at this point, we essentially have our whole optimization. We just need to describe each of our variables. So for starters, Tt max, well, that's in reals, right? And then we have Tti, right? And that's also in reals, where I is from 1 to n. Okay, so this is the takeoff time for each aircraft I. The last set of decision variables that we have are these binary variables. And so here we would say, well, Bij is in the set of 0 or 1. Or you could also say equivalent. Instead, you could say binary. If you want, you could write it like that. It's the binary set. And this is true for all I, again, I less than j, where I and j index over all the aircraft, so the n aircraft. And there we have it. We've just written an optimization program that will minimize the time it takes for us to take off n different airplanes. Okay. So at least structurally or notionally, this is how you'd write such a program. You know, you could even add additional constraints associated with each binary variable. There's no rule about that. Okay. So this is just one specific example. You know, if we want to generalize this, we could absolutely generalize it. So again, let's say we add some max or minimization. Right? Where X is built up of maybe some real variables and some binary variables. And we have some sort of statement where if some binary variable is true, then we're going to say, well, some set of linear equations has to be true. And if it's not true, so let's say some binary variable is 0, then maybe we have a different set of linear equations that have to hold true. And in fact, that's what we did in this previous formulation, right? We said, well, if the binary variable is true, then this linear constraint holds true. And if the binary variable is false, then this linear constraint holds true. And again, we could rewrite, we can write this as sort of like an AX is less than or equal to B if we wanted to. Right? Now here, I'm saying we can generalize that. So like, again, if X is multidimensional, it's not just here we had one constraint, we could have like 20 constraints associated with a binary variable being true or false. So again, in that case, you know, when we have our list of decision variables, and we might even have a set of linear constraints that are true for all X and Y, regardless of whether a binary variable is true or not. Okay. So essentially what we're doing is we're turning on and off constraints based on a set of binary variables. Okay. So again, the question becomes, well, this is essentially a nonlinear problem because of this introduction of the binary variables, right? So the moment we see binary variables, we should think our decision set of feasible space is non-convex, right? So normally, you know, convex sets, we pick 2 points and we can connect them. But here, if our decision variables lie on 0 or 1, right? So we can be 0 or we can be 1. We can't really have 0.5, right? So this tells us that, you know, having a decision variable that's binary is non-convex, right? So we're going to try to find a way to, you know, there's not much we can do about that, right? It just is what it is. And so solvers like CPLEX, again, have trouble dealing with non-convex problems, although it can certainly solve an integer or binary problem. Sometimes we have to do tricky things in order to get it to work, especially when these binary variables turn on or off sets of constraints. Right? So let's sort of see how we can implement this logic into a linear program. All right. So what we're going to want to do is we're going to want to see, can we represent what we have above as something that looks a little bit different, that looks more like a linear program where we don't have this if statement, right? So what we're going to want to do is we're going to say, well, we still want AX is less than or equal to B because that always holds true, right? No matter what a binary variable is. But maybe we want to do something where we say AIX is less than or equal to BI. And AI tilde is less than or equal to BI tilde. But we only want this to happen when the binary variable let's say xbi is either true or false, right? And the trick that we're going to use is something called the big M method. I know we've already studied something called the big M method when it came to like using the simplex method. This is completely different. Okay, so if you Google search big M method, it's hard to find stuff on it because usually if you search big M method, you get stuff on you know, what we did with the simplex. But we're going to introduce this idea called the big M method, where the way we implement this if-else logic with the binary variables is by having a large value m times xb, right? And we're going to add it to the right-hand side of the first constraint. And we're also going to have m times 1 minus xbi for the second constraint. All right. So let's sort of see how this works out and why it works. All right. So the neat part is this can be programmed in Cplex pretty much easily. Which is to say, you could actually write this as maximize, you know, C transpose X such that, let's say we have some super A, X is less than or equal to some super B, where this super A and super B actually accounts for all these equations. Okay, and so you can write this in Cplex, which is really, really neat. All right, so let's sort of see how that happens. No, actually, well, okay. So I want to focus first on when xbi, so we have some binary variables equal to 1. Right? Why does xi plus bi plus mxbi? So what I'm claiming is that these two statements, right? Well, actually, what I'm just saying is this statement here, right, is equivalent to what we had before where we said, hey, if xbi equals 1, then AIX is less than BI. Okay. So how are these two statements true? Well, let's sort of look at what happens. And actually, I might have written, did I write this backwards? Actually, I wrote it, sorry, I wrote this a little bit backwards, but we'll work through the logic. And we're actually going to study two of the equations. What did I feel like? Oh, okay. And I did write these backwards. I'm almost certain. Okay, so we're going to look at it when xbi is equal to 0. Okay. All right. So let's see what happens when xbi is equal to 0. So we can just plug in 0 for xbi. In that case, this first equation devolves to xi, or ai times x is less than or equal to bi. Okay? So that's kind of the constraint that we wanted, but it's a little bit different because our binary variable is flipped. Before, we wanted to do something where xbi is equal to 0 implies that ai times x less than bi holds true. Okay, so we kind of flip this around a little bit. If we want it to work better, well, we'll see sort of how we can work it better. But for this second equation, if we plug in 0 for bi, then we end up with xi tilde, or a tilde I times x is less than b tilde I plus some big value m. Okay. Now, what this means is that this second equation, right, because m is a large number, very large number, if xbi is equal to 0, this holds true easily. Oops, what's going on?
So Dr. Vela, it is 1 minus xbi, right? Not 1
Yeah.
minus bi. Second equation.
Yeah. Can you hear me right now?
Yes.
Okay, because my computer just froze.
No. For second equation, it is m time 1 minus xbi or 1 minus bi.
Hold on. Sorry, I'm gonna have my computer completely froze.
Oh, okay.
So, oh jeez. Okay, let me. My computer might be overheating, unfortunately. I'm gonna exit Zoom and then try to rejoin Zoom. Hopefully, it's just a small issue. So if you get kicked out of this meeting, just try to rejoin in. My apologies again. My computer, I think it's overheating or it's frozen. I can't write anything on my screen or do anything. So I'm going to try to restart Zoom and worst case scenario, restart my computer, which it looks like I might have to do because Control-Alt-Delete is doing nothing. Okay, so I'm going to restart my computer right now, guys.
Okay.
Please rejoin if you can.
Thank you.
Oh man, this is bad. we're going to give this another try. I think I'm still recording, but just in case, let me do another recording. Okay. All right. All right. So I think your question, El Sahid, is here I'm substituting in xbi is equal to 0. Okay. So when we plug in xbi equals to 0, this goes to 0, while this quantity goes to 1. Okay. And what that means is that essentially this first constraint holds. It's sort of enforcing the constraint, okay, of AX is less than or equal to BI. For the second constraint, because when we substitute in XBI equals 0, we're left with this plus M term that's very, very large. And so it automatically holds true. All right. Now, we can look at the opposite case when BI is equal to 1. Then we get sort of a flipped scenario. Right? So it's a little bit backwards than we'd want, but that's okay. So let's say, again, we have AX is less than or equal to BI plus M XBI. And we have AIX is less than tilde BI. So it's a different set of linear equations. 1 minus XBI. Okay. So when XBI is equal to 1, this part right here is just going to be equal to M, this whole thing. Well, this part goes to 0, right? So everything here is going to be equal to 0. That means the set of equations is going to be equal to AIX is less than or equal to BI plus M, and A tilde IX is less than or equal to B tilde I, like that. And so what that's going to mean is that this constraint is easily satisfied. Right? Because it's got this big value of M. Right? While this second constraint is, we'll say, tight, right, in some ways, and enforces the desired constraint. Okay, so let me give you like a practical example of this. And I'll sort of flip the logic to be a little bit easier. All right. So we'll just do a quick one. Maximize C transpose X such that if, I don't know, some binary variable is equal to 0, then 5x1 plus 3x2 is less than or equal to 2. And maybe we'll have x1 plus x2 is less than or equal to 3. Alternatively, else, if xb is equal to 1, then we're going to have a different set of constraints. So maybe it'll be 10x1 minus 2x2 is less than or equal to 4. And again, our decision variables are x1 and x2 are reals, right? While xb is a binary. Okay. So practically, how do we program this in Cplex, right? Or something that looks more similar to Cplex using the technique that I just described, right? What we can do is we can start by saying, well, what is our, we'll call this A1 and B1, right? So this A1 is just equal to 5, 3, and 0. And then it'll be 1, 1, and 0. Okay, so what are these different, what do these zeros correspond to? Well, and what do the numbers correspond to? Well, this column is multiplying times x1, which makes sense. This column is multiplying times x2, all right? And in fact, sorry, this shouldn't be 0. Well, we're going to put it as 0 for now, but then we'll augment it. We'll sort of fill in some stuff. This will be times our binary variable. Okay. Similarly, for our B1, we're going to have 2 and 3, right? Because we have 2 constraints here. Right? So for the second set, let's say we have A1 tilde. We're going to have, it's just going to be one row, so 10, -2, 0, and B1 tilde, oh, yeah, B1 tilde is going to be equal to 4. So the way this gets written up is as follows. So we still have maximize C transpose X, whatever that used to be, such that, right? Now, I'll go through this series of steps in order to get it the way that we want, but we're going to have 5, 3, 0, 1, 1, 0 times x is less than or equal to 2, 3. Okay. But we also have this big M component, right? So let's say this big M, so I'm going to pick a really large value. So let's say 10,000 times XB and 10,000 times XB. Okay. Now we can move this over, right? So this quantity right here can be moved over to the other side because it's the decision variable, right? X, right? So our X contains X2 and X, right? So you just have to be a little bit careful when you do it, but you can sort of work it out. So when we move it over, we no longer need to write this stuff over here. Instead, we're going to erase the 0 and 0, and we're going to put in 10,000 and minus 10,000. Okay. We can do the same thing for what happens when XB is equal to 1. All right. In this case, we would have 10, -2, and 0. But keep in mind this 0 is going to change. It gets multiplied times x. Right? It's less than or equal to 4. But now we have to do this 1 minus m times 1 minus b. So we would write that as, let's say, 10,000 plus 1 minus x b. Okay. So if we're going to convert this where we have all our decision variables on one side and all our constants on the other, the way we end up writing this is, again, we're going to delete all this stuff, right? Or at least where we can, and we're going to move this 10,000 XB to the other side. Right. Now we still have another term here, which is from this 1 times 10,000. Well, we can just add that in right there. Okay? So what we end up in this case is we end up with 10,004. All right, let's put this all together. So we have maximize C transpose X subject to five, 3, negative 10,000, 1, 1, negative 10,000, 10, negative 2, 10,000. That's one big matrix. Well, not really big, but you know what I mean. We're joining a bunch of matrices together. Times X is less than or equal to 2, 3, 10,000, and 4. Where X1 and X2 are elements of reals, and we'll say XB, which corresponds to the third variable, that's a binary decision variable. Okay, so this problem you could actually implement in Cplex very easily. Right? And what you'll see here is I don't have these if statements running around. Right? So before, I had these if statements, if xb equals to 0, if xb equals to 1. By using this big M technique, we can actually write our mixed integer linear program where we have these binary variables as what sort of looks, in our standard form that we're used to, which is ax is less than or equal to b. We don't actually have to implement this if-then logic. Okay, so that's really nice. Okay. What we're going to do is I'm going to take a quick, we're going to take a 15-minute break, right, until 3:10. So unfortunately, my computer is overheating. That's why I had to restart. And so I'm hoping that with this extended break, my computer will maybe cool down a little bit if I stop the video. And then we'll continue at 3:10. Unfortunately, if my computer continues to overheat, then we might have to stop lecture, and I'll have to record it later and post it. But this seems like a good point in time to take a little break. So again, let's reconvene at 3:10 in 15 minutes.
May I have a quick question, please, Dr. Villa?
Yeah.
I'm sorry, I joined late, but so in binary system, so the maximum variable could handle it is 2?
No. Oh, yes. So don't think of it in terms of the number of binary variables you can handle. The binary variable just tells you think of it as, well, look, it can handle as many decision variables as it can. It's more about how many sets of constraints can it handle. So here you have 2 sets of constraints. All right. If the binary variable is 1, then 1 set of constraints holds true. If the binary variable is 0, 1 set of constraints holds true. If the binary variable is 1, then a different set of constraints holds true. That's really what matters.
Okay.
It has nothing to do with how many decision variables are in those equations.
I get it. Thank you.
Yeah. Okay, so let's go ahead and take a break, and I'm going to stop the video meanwhile. I'm gonna get started in about a minute or so. Just let some folks trickle back in. Okay, we're gonna go ahead and get restarted. Let's see. Saeed, can you hear me?
Yes.
All right, perfect. Okay, so all right, so I want to sort of summarize what we've done. So the basic idea is if we have some sort of maximize or minimize optimization problem where we can define constraints that either get turned on or turned off by binary variables, we can map that into something that looks like a standard LP. Right? So what I mean by that again is if we have something where we have some binary variable equals 1, that maybe we have a set of linear equation that holds true, right? And we could even have multiple binary variables where, oops, I'm gonna say this too. Then we have other sets of linear equations. And you can note that we don't even require that we add linear constraints if the binary variable is false. So maybe we say, well, if x2, the binary variable, the second binary variable is 0, we have a different set of linear constraints. Right? So that's what I'm kind of doing here. You'll notice the way that I wrote this, we just said, well, if xb1 is equal to 1, then we have a set of linear constraints. We don't say anything about what happens if xb1 is equal to 0, right? Well, for the later case, here we say, well, if xb2 is equal to 1, we have one set of linear constraints. But if it's equal to 0, then we have a third set of linear constraints. We can even do really funny things where we can say, well, let's say if xb3 is equal to 1, maybe we have a third set of linear constraints. Okay. So here goes our third block, and we can maybe even have an else, right? So if xb3 is equal to 0, oops, and this shouldn't have a tilde. We have, another set of linear constraints. Right? We could even say something, well, xb3, well, that is equal to 1 if, let's say, I want to make it sufficiently complicated. I just had an idea. If both, so XB3 can only be true if XB1 and XB2 are true. And so you can do that by saying XB3 is less than or equal to XB1 and XB2. And so essentially what this is saying, well, if either one of these values is 0, then XB3 has to be equal to 0. Now the question becomes, how do we force it to be 1 if XB1 and XB2 are 0? And so the way that we can do that is we can say, sorry, I just thought of this on the fly, 1 minus XB1. Yeah. So we can say something like 1 minus XB1. Oh, no. Oh, shoot. If they're both true. So I want to do something like this. If XB1 and XB2 is true, then XB3 has to be true. Okay? Just had this in my head. How do we do a logical AND? Not true. Yeah. Well, we'll come back to that, I guess. So let's come back to that idea in a second, because it's a little bit more complicated than I thought. Either way, we can have multiple sets of these binary decision variables turning on and off different sets of equations, okay? And that's the whole idea of how we can use these binary variables as part of a mixed integer linear program. Now, we've already sort of dealt with binary variables when we were doing these assignment problems. Now, we can actually make more complicated assignment problems than we have in the past by formulating them as binary variables, to use binary variables. So let me give you a quick example of that. Let's say we were doing some sort of like fantasy football. Right, or fantasy baseball. And essentially you have n players to pick from, and you have m skills that you rate those players. Okay. And your goal is basically your decision variable is going to be this xi, which is a binary indicator variable. Right? To indicate if player I is selected for your team. Right. Now, in order to solve this problem, we're going to have to be given some information, right? So we're going to be given a matrix Sij, where the value Sij corresponds to player I's ability at skill J. So how good are they at, running, right? How good are they at catching? How good are they at defense? How good are they at center snap, right? And so we have these skills that we're going to rate the players across. Right? So essentially, we have something that looks like the following. So we have we have the different skills, S1, S2, S3, across the board, all the way to SM. Right? And then we also have a set of players. Okay. So P1, P2, all the way to PN. And within these, we're going to have values, right? So we might have 0, 0.5, 10, 0. So, you know, this player isn't very fast, but they're really good at playing quarterback or kicking the ball, right? So every player will have some sort of vector describing their skills. Okay. All right. One of these, let's say we might even include it. Let's say one of these variables, right, might even be their like contract cost, like how much money they cost to get them on your team, right? So there's all sorts of skills, and maybe S1 is how fast they are, all right? And S2 is how many points they score per game, right? So again, these variables, they can be arbitrary, but they're some sort of measure of the particular player, right? We could even say, you know, maybe we have another matrix, right? Where we talk about, well, Cij, which is the benefit of the skill towards winning games or matches, whatever you want to call it. So this is like the idea of Moneyball. Like, okay, RBIs are most important, so we're going to weight those more. So we could do something like that. So within this context, we can define some sort of optimization where you say, well, we want to maximize our expected, you know, total benefit of these skills by double summing over I and j of Cij times Sij, right? So this is the benefit. This is the skill value, or the skill rating. Actually, this should be, really this should be Cj, sorry. Because we don't have a different benefit for each player. We have a different benefit for each skill. All right. And then we're going to multiply that times Xij, which is the decision variable on whether we draft a player. Draft player I. Okay. All right. And of course, we can subject that to some constraints, right? So we might say something like, well, we need to make sure we have at least 20 players on our roster, right? So the sum over 1 to n has to be equal to 20, right? We could also say, hey, maybe we need our salary to be less than $20 million. So here I said salary corresponded to the third column. Right? So here we would say SI3 times X3. Well, if we sum up all the drafted players, that might need to be less than $10 million, right? Or, you know, whatever, $1 million per year. Okay. We could also say, hey, maybe we have some minimum required collective skill, right? So we need them to at least score so many points per game, right? So I think that was S2, right? So we could say the sum of I2 times X of I is greater than 20. Okay. So this is a really neat way that we can use binary variables, right, in order to solve a problem. So here it's just a more complicated assignment problem than what we're used to, but we can take into account a greater number of factors. Now, there are really, really neat ways that we could sort of combine binary variables. So we might also have constraints that tell us, hey, two players can't play on the same team. So you have to get one guy or the other, right? Or you have to at least get, you don't need to get, you need a star quarterback. So you need to get Tom Brady or, I don't know, who's another quarterback? Aaron Rodgers, right? Sorry, they're just in the news, so I remember them. And so how would we account for those sorts of ideas, right? One way we could do about, so let's say we had two binary variables, and I'm just going to call them B1 and B2, where B1 and B2, again, they're binary variables, 0 or 1. So the idea is, well, how do we make up different type of constraints to represent an OR constraint or an AND constraint? Okay. So one way we could do, let's say, an AND constraint. Well, we'll start with an OR constraint. Okay. So that is to say, either B1 is true or B2 is true. Well, we would say B1 plus B2 is greater than or equal to 1. Okay. So you have to get one of those players, right? Now, an AND is actually less interesting than you would think, because if an AND is true, if we have an AND statement where B1 and B2 have to be true, then effectively we're saying B1 is equal to 1 and B2 is equal to 1. And so there isn't really a decision here. All right. At least in this case, we had a decision, which was you have to get one or the other or both. Okay. An AND constraint doesn't have a decision involved with it when we program this up. Another thing that we could program is an X-Nand. Okay. So this idea is that one or the other is true. So the way we'd write this is B1 plus B2 is equal to 1. Right? So either B1 is equal to 1 or B2 is equal to 1, but not both. So in the previous example, this might be if you have two players, but they don't get along. Right? You can draft one of them, but not both of them. But you have to draft one, right? So you have to draft one of them, but you can't draft both of them. Alternatively, we could do NAND. Right? So a NAND corresponds to B1 plus B2 is less than or equal to 1. So again, this is the idea of both can't be true. Okay, so you can draft player 1 or draft player 2 or not draft either of them, but you can't draft both of them. So that would be the kind of equivalent. Another good one is Xnor. Right, so this would be x1 minus x2 is equal to 0. Right? This basically tells you both are either, not x, b. So b1 minus b2 equals 0. This is the same thing as just writing B1 equals B2, right? So either they're both true or they're both false. There are really neat ways that you can combine a bunch of binary variables. So there's this idea of zipper constraints. Okay. And the way we write a zipper constraint is as follows. So let's say we have a bunch of binary variables. Okay. A zipper constraint often takes the following form, where we say B1 is less than B2, B2 is less than or equal to B3, B3 is less than or equal to B4, and so on, all the way down to Bn minus 1 is less than or equal to Bn. All right. So why is this called a zipper constraint? Well, it has this property that once one of the binary variables becomes true, then all the subsequent binary variables become true. So for example, let's say B1 was equal to 0, and B2 was equal to 0, B3 was equal to 0, and then all of a sudden, for some reason, B4 is equal to 1. What that's going to do is that's going to force B5 to be equal to 1, B6 to be equal to 1, and in fact, all the way to Bn is going to be equal to 1. This becomes really neat if these binary variables turn on or off linear constraints. The reason it's called a sort of a zipper constraint is, you can think of it as like, it's sort of like the zipper gets tightened, right? Or in some ways, right? Like once it becomes true, then you're starting to cinch down on the values. So that's sort of a neat one. Let's see if there's another one I wanted to address. Give me 1 second. Or a minute, actually. Okay. All right. The other constraint that I started to allude to, but I kind of got mixed up, and so I want to bring it back up, is what if we want something where if B1 plus B2, or actually let me rewrite this. Let's say B1 is equal to 1 and B2 is equal to 1, then this is going to force B3 to be equal to 1. Otherwise, right, so in all other conditions, B3 is equal to 0. The way you actually want to think about this is a little bit backwards, though. Okay, so this actually works in both directions, if you think about it. So the way that we could write this is we could say, well, if B3 is equal to 1, then B1 plus B2 is equal to 2. Right. alternatively, if B3 is equal to 0, then B1 plus B2 is less than or equal to 2. Okay, so here, now what we've done is we've set up a set of linear constraints based on the value of B3. So it works a little bit backwards than what we expected. But using the techniques that we described above, we could actually program this using a big M method. Okay, so let's sort of talk about a big M method. And in fact, we could, I think to maybe El Said's question, right? It could, there's no rule that says how many variables have to be involved. So maybe we could make it 3 binary variables, right? Oops, less than, sorry, that should be less than or equal. Okay, so maybe we have something like this, right? So we have this binary variable B3 that, depending on if it's 1 or 0, that sort of forces the values of B0, B1, and B2. Okay. So if B1 is 1, then B0, B1, B2 have to be all true, right? Otherwise, not all of them can be true. One of them has to be false. So this is a neat little problem. And again, you sort of have to think about the logic, and sometimes you'll have to work a little bit backwards. But we could definitely program this in the sort of form of AX is less than or equal to B. So let's sort of see how we would do that. Okay, so here I'm going to define the X to be B0, B1, B2, and B3. Okay, so let's look at how we would do this with the big M. Right? So we would want something where B0 plus B1 plus B2 plus B3. We want this to be true, right? And we can actually, we're going to have, one way that we could do this, because we're doing this less than or equal to, we're going to have to sort of write the equal signs 2 different ways in order to pinch it. So if we do it that way, then we have to multiply times -1 by everything. And so these all turn to minus signs. Okay. So there we go. So if we want to turn this into a big M, the way we do that is we'd say, well, we're going to add plus M times 1 minus B3 plus M times 1 minus B3. Okay, so what we're doing here is when B3 is equal to 1, essentially this stuff gets deleted and we end up with B0 plus B1 plus B2 plus B3 is equal to 3. Okay, now we want to allow for this other case. Well, what happens if B3 is equal to 0? Then we need to make sure that B0 plus B1 plus B2 is less than or equal to 2. So the way we'd write that is we would just write our constraint B0 plus B1 plus B2 is less than or equal to 2 plus M times B3. Okay, so let's see what happens here. If B3 is equal to 1, right, then M, because it's a large value, makes this whole thing look something like 10,002, right? So obviously B0 plus B1 plus B2, because they can only be the values 0 or 1, they're easily gonna be less than 10,002, okay? But if B3 is equal to 0, right, then we're left with just this part of the equation that's gonna have to be constrained, right? If B3 is equal to 0 here, then we easily satisfy our big M constraints. Okay. So in the end, this set this logical definition, right, of, hey, if B3 equals 1, then B0 plus B1 plus B2 is equal to 3. Else, if B3 is equal to 0, that B0 plus B1 plus B2 is less than or equal to 2. We could replace these two guys with the following linear constraints, and these two are equivalent, okay? And we can write these up. Oh, I don't know why I included B3 here. We can write these up in Cplex. Right? Again, if we want to put it in this AX is less than or equal to B form, we're going to have to move the B3s over to the other side. Right? So we would get B0 plus B1 plus B2 plus M B3 is less than or equal to 3 plus M. For the next equation, we'd get B0 minus B0 minus B1 minus B2 plus MB3 is less than or equal to negative 3. Oh, plus M. Okay. Right. And then finally, for the last equation, we'd get B0 plus B1 plus B2 minus MB3 is less than or equal to 2. Okay, so now we can put this in sort of the AX is less than or equal to B form. And here our A is equal to 1, negative 1, 1, 1, negative 1, 1, 1, negative 1, 1, and then, you know, M, which is some big value, M, negative M, right? And our B vector will be equal to 3 plus M minus 3 plus M and 2. So one big question that we get a lot of times is, well, what does the value of M have to be equal to? Okay. Really, it's sort of an, I mean, there's no like easy way to do it or straightforward procedure, but essentially what you're trying to do is you're trying to look at the range of the values that you get within the constraint, okay? So here, I know that the B values are going to be between 0 and 1. So the smallest that B0 plus B1 plus B2 could be is 0, and the largest that it could be is 3, okay? So practically speaking, as long as I'm bigger than that, you know, like I could pick M equals 10 and that would probably work out fine. Okay, it doesn't have to be like 10,000 or 10 million. But really what you want to do is you want to look at the range that these values can take on and just make sure that you're safely larger than whatever that range can be. Okay, and you'll be okay. All right. So again, you know, I started off with some statement of, hey, I want to represent this idea that if we have 3 binary variables and they're all true, then a 4th binary variable is true. Okay, and I want this to map back and forth. And so the way that I did it is I said, well, let's start by formulating it as an if-else statement. And then we can translate it that into something that looks like AX is less than or equal to B. And so it took a little bit of effort, but I could do it. Okay. So you could just add this in to your overall constraints. All right. With that, maybe it's worth revisiting where we started. Right? So where did we start? Okay. Is this it? Nope. Where's my airplane problem? Yeah. So here goes our airplane problem. We can think about, well, how do we actually write this in the form that I was talking about? Okay. So I'm going to oops. Well, okay. So again, the idea is we want to change all this stuff into something that looks like minimize C transpose X subject to AX is less than or equal to B. And this, you know, the standard form that we've been working with for a while. Now at this point, in order to do this, we need to define what our X decision variables are. So this is pretty easy. In this case, X, you know, we have our TIA1 all the way to TIAN, right? Which was the adjustments to when we push back each aircraft. We also have decision variables about the time that each aircraft took off. I should draw this a little bit more open-ended. After that, we have the maximum time, right? The decision variable according to the maximum time. And then finally, we have these BIJs, right? That correspond to the order that the airplanes are going in. So we're going to have B11, B12, all the way to Bn-1 to n. Okay. So this is going to be our decision variable. Within this framework, figuring out what our C is actually pretty easy. So C is just going to be C transpose. We're going to have a whole bunch of zeros, right? But then we're going to have a value of 1 where T max is. So we're going to have something like this. All right, so how many zeros do we have? Well, we have 2n of them. And then we have the value of 1. Right? And then we're going to have a whole bunch more zeros. I forget what the equation is to count that, but there's some sort of, you know, combinations or permutations equations that we could sort of figure out. Okay, so that's pretty easy. The next thing that we want to deal with is, well, how do we put this in matrix form? Okay, and we've done this before, right? When we are talking about nonlinear and linear equations. Right? So let's sort of, I'm going to pull this aside. Okay, and what I'm going to do is I'm going to sort of set this up so we can have like multiple A matrices, and then we'll just stack them together. Okay, so for this guy, it's, you know, if we were to think about what these equations are doing, we want to move all these T's to the other side, right, for this particular problem. Oh, and actually, I don't want that. Okay, so for this particular, you know, I'll call this A1, which is just one set of the linear equations, right? So if we look at what happens, we don't have any of this stuff or any of these other things in there. So our A matrix we're going to have a whole bunch of zeros, okay? And I'm going to sort of demarcate this just so we can follow along. So I'll put 0 here. And again, this corresponds to all the time adjustments. Okay. But what we do care about is we have these T's on this side. And so we're going to end up with an identity matrix, okay, that's going to be multiplying times all the T takeoff times. Okay. It's going to subtract -1, so this is just a row vector corresponding to TT max. Right. And then it's going to have 0 for all the binary variables. Okay. Now we do need to, we do need to sort of address what is the B. Well, in this case, we see that once we move over all the decision variables to the left, we're just left with a whole bunch of zeros. Okay. And so we end up with n rows like this. Okay. So that's our A1. Okay. So what's going to end up happening is, so if we think about this A is going to be a stacking of different matrices. Okay. All right. Okay, so what's our next constraint equation? Well, our next constraint equation has to do with calculating the takeoff times. Okay. So let's sort of copy that down. So this will define our second A2 matrix. Okay. So again, if we want to think about, well, how does this break down to our A matrix? Our A matrix comes in 3 different parts. Okay. These 2 guys are constants, so we're going to keep them on the right-hand side. And in fact, probably what we want to do, again, because we want it to be AX is less than or equal to B, we're going to have to do a minor manipulation of this equation. All right. So what we're going to do is we'll put all the constants on one side and all the decision variables on the other. And so when we do that, we get TAI minus TTI is less than or equal to TBI minus TTI, which was the taxi time for each aircraft. Okay. So this makes it really easy in order to calculate our B's and our A's. So the B's are just, again, minus TB1, minus TT1, right? And this goes all the way down for the N aircraft. Okay, so you can calculate that. Again, these are usually given, these will be given values if you're to have this problem. All right. Now the problem becomes, well, what's this A matrix? This is a little bit harder to figure out, but it's not too bad. Right. You're going to end up with an identity matrix that corresponds to the TAs. Right. You get a so the takeoff times are the next set of decision variables, right? So you're going to have another identity matrix, but it's going to be a -1 going across the TTs, right? We don't use TT max, right? So we have a 0 here, and we don't use any of the binary variables, right? So again, we have a bunch of zeros there. So now we have, you know, a matrix, right, for our second set of constraints, so A2 and B2. And the last set of constraints that we have to deal with are these logical binary constraints. Okay, I'm going to copy this down, and we're going to try to represent this as, again, AX is less than or equal to B. And this might be a little, this actually is going to be quite challenging because we're going to have multiple B matrices and stuff like that. Okay, so this is far from easy, right? So I don't want to say that this is easy in any way. I think the first 2 sets of constraints that we developed, well, that was a little bit easier to work with. Okay, but this is a little bit more challenging. Okay, so we want to convert this into this, like the big M equation that we were doing before. Right? So again, this is a little bit backwards, but we'll sort of work through this. Right, so I'm going to start with this bottom equation here. So we're going to want to say if this constraint is true if Bij is equal to 0. So the way we would write that is as follows. Okay. So if Bij is 0, then it's like this thing disappeared and the constraint holds true. If Bij is 1, then that constraint easily holds. Okay. Now we need to include this other constraint. Right? And here we would write that as TTI, plus delta Tij is less than TTJ. Now this constraint is true when Bij is equal to 1. So here we would write m minus 1 minus Bij. Okay. So these two equations are equivalent to what we see here. Okay. So they're perfectly equivalent. Okay. All right. So at this point, we need to put this into this AX is less than or equal to B form. In order to do that, we have to move some of our decision variables around. So we have to move these Bij's to one side, and we have to move these T's to the other side, because these are all constants, right? So if we were to do that, we would end up with TTJ minus MBij is less than or equal to TTI. Oops, and I feel like one of these should have been lowercased. Man, what did I mess up on? TT, yeah. No? Did I do something? Oh, no, that's right. Okay, sorry. TI, T. And then we need to subtract off delta T, J, I. Okay. For the second equation, when we move everything over, we end up with TTJ plus MBij is less than or equal to TTJ minus delta Tij plus M. Okay. Alrighty. Now, again, these are all equivalent equations. And here we have all the decision variables on one side. And on the right-hand side, we have constants. Okay. So we will have this equation for each binary variable Bij. Likewise, we all have this equation for each binary variable Bij. Okay, so we're going to have these equations come up over and over and over again. All right, so the best way that I sort of think about it is, well, let's figure out what is the A3, and I'll call this A31 and B31. Right? And we'll make this a second submatrix, A32 and B32, where A3 is the stacking of these two guys. Okay. All right. So let's sort of work this out. We have A31. Right? And again, we want to think about what are the decision variables that we have in our matrix A. It's the TA, TT, Tmax, and Bij. Okay, so I'll sort of write those out. TA, we then have the TTs, the TT max, and then finally the Bij's. Okay. Right. So if we look at our first equation, we see this TT times J, right? And this is going to repeat for every IJ that we have, okay? So essentially what we're going to end up with is sort of like an identity matrix. Right? We're going to end up with a minus m times an identity matrix here. Okay. And then we'll have 0 everywhere else. Right? And for B31, you know, we have, oh, oops, sorry. Oh man, I messed up. I shouldn't have done that. This is a decision variable right there. Man, I can't believe I did that. And this is a decision variable. Okay. Okay. All right. So this actually ends up being a little bit weirder than I thought. Okay. Okay. So either way, you're going to end up with something that sort of looks like an identity matrix there. And for this, these TT, so you're going to have 0 here because you have nothing to do with TA. Here, what you're going to see is this pattern where you end up with something like 1, minus 1, 0, 0, 0. 1, 0, minus 1, 0, 0, 0. 1, 0, 0, 0, minus 1, right? Because you're taking the differences between variables that are all greater than it. And then you're going to do 0, 1, 0, 0, 0, or sorry, 0, minus 1, 0, 0, 0, right? 0, 1, 0, negative 1, 0, 0, 0. 0, 1, 0, 0, negative 1, 0. And so it's sort of this pattern, right? Where you get a bunch of 1s and then a minus diagonal of minus 1s going across, all right? So 1s, diagonal minus 1s, right? 1s, diagonal minus 1s. And so we're going to keep following this pattern all the way through until we get, and in fact, this is 0. We get 0, 0, 0, 1, and you get a minus 1. Okay, so this is actually a bit of a complicated matrix, but you can make it. And then we have 0 here, we have the M, and finally we have the B31, which is just given by the TIJs. Okay, so you're going to have to go through these. So it's minus delta T11, minus delta T12. And it goes through every single one of them until minus delta T n minus 1 n. Okay. This is very complicated. And in fact, the whole point of doing this is that, yes, we can end up with a problem where we write it as AX is less than or equal to B, but this A matrix and B matrix gets really, really ugly. So in fact, you're better off using Cplex and these types of equations using the for all or the for loop in Cplex. Okay, because what you can do is instead of writing your problem as like this, AX is less than or equal to B, you can loop over every I and every J and write out the equation. Okay. So that's it for me today. Again, I want this whole point of this exercise was to show you, I know it's a little backwards, that you need to watch the other videos on Cplex and how to do a for loop. Otherwise, you're going to be stuck making these huge, hideous matrices, right? that, well, technically, yes, you could read it into Cplex. You're going to spend more time making these matrices than you would if you just programmed it in Cplex. All right, so with that, I am done. This is technically our last lecture, but what I will do is, moving forward, I will use this time as office hours, where folks can ask me questions about the project or if they have issues with Cplex. Again, just like with regular office hours, I ask that you please send me a quick message if you want to attend. Probably what I'll do is I'll start this office hours at 1:30 until 2:30, and if nobody comes, probably in the first hour or so, then I'll probably just drop off. But you can always message me and I'll jump back on. So again, moving forward, this is our last lecture. Everything else is Cplex programming, which again is better off done in the videos, I think, than during lecture. So if that's it, we'll end lecture. We'll end our lecture. Are there any other questions?
I have a question for Simplex, not for the question,
Yeah.
not for lecture. I don't know why when I make a Simplex with objective function as a maximize, as a minimize, doesn't work. But when I change objective function as a maximize, doesn't work.
Oh, that probably means you have an unbounded problem.
Mm-hmm. Yeah, okay.
Yeah, so that's probably what it is. I mean, I think the bigger point is, why does it make sense to minimize or maximize? Which one are you supposed to be doing? A minimization or a maximization?
I should be minimization, but
Okay.
it doesn't work. When I change maximization, give me answer. When I make
There's nothing that should prevent it from working. That I would have to see your code.
okay, in office
Yeah.
hour. But
Yeah.
the office hour, no afternoon office hour, all of them is 1:30 because I know.
No, so I still have my same old office hours as before. So
Because
you can come then, but again, if you want to come to office hours, you just have to send me a quick message.
But it as no, not at 1:30. It's from 5 to 6 or from 1:30.
I don't know. There's a bunch of different office hours.
Okay, I got that.
There's office hours on Monday, right? From
Yeah.
I don't know, what is it? 5 to 6? Or
Yeah.
no, 6 to 7.
Yeah, this one works with me. Yeah.
Yeah, whatever the office hours are. Right? And then there's an office hours on Thursday from 11 to 12. And now there will be extended office hours from 1:30 to 4:20.
Oh, more than enough. Okay.
Yeah, more than enough. Exactly.
Yeah. Thank you, Dr. Fell.
Yeah. Okay, if that's it, we're gonna stop. See you guys. Thank you.
Thank
Bye.
you, Professor. Have a good one.